Hello everybody and welcome to Handmade Hero, the show where we code a complete game live on stream. We have to improve our lighting quality today. I think we debugged most of the weirdness that was going on yesterday with the lighting flicker. And today we have to start dealing with the fact that we would like to produce good lighting results without introducing flicker from our sampling. And there's a lot of ways we can do this. There's a lot of things that we kind of need to start looking at. The primary thing I want to start with, because what we were having trouble with at the end of yesterday, is I want to start trying to get to a place where we can have good balanced lighting. So basically, like, I want to start to be at least slightly more rigorous in understanding how light is put into the system and how it drains out of the system. And right now we don't really have a very coherent way of looking at that. And it's a fairly confusing problem because you're trying to come up with an approximation for something, and your approximation is going to be nothing like what the real thing is doing. Because again, I said this before when we started, with lighting, you're talking about a process that the real world uses, billions or trillions of particles to evaluate. And we are talking about thousands or tens of thousands of particle equivalents that we have to use to evaluate. And so basically, the fundamental way in which we look at the problem has to differ from how nature does it very dramatically, because we need to carry so much more information for every one of those particles than nature does, right? So we need to kind of be very aware of all of the ways that we can try to sacrifice some of the accuracy without sacrificing apparent visual quality as we change over the nature of the computation from what we know to be correct to something that is incorrect but still pleasing. And that's a very difficult thing to do because you just don't have nature as your guide, right? When you're simulating something and you can afford to do a good simulation of it, you're actually, although the cost to you may be high in terms of learning and math and understanding of the problem, you kind of do have a nice benefit, which is that you are looking to nature, the thing that you actually wanted to replicate. You are looking to it as a guide, and it can guide you. In our case, we really can't do that. We are looking to create a sort of parallel process that is very different from the way that it actually would be computed. And that's why it's a very challenging sort of approximation to develop, because it is so far afield from what's actually happening. So I see there as being a couple important things that we need to focus on now as we try to improve the quality of how we're doing our lighting transport, given the low number of samples we get to take. So what we effectively want to compute is, a very simple, going back to the original problem, is actually fairly simple, right? It's just sort of a series of these bounces. If I've got a surface here and I'm trying to compute the lighting at this point, so this is my sample point for the lighting. And no matter how we structure it, even if we drastically change the way that we're doing our sample points, how they're distributed, what they mean, whatever, we're still always going to come back to this exact fundamental problem, which is that at the sample point, we fundamentally want to have a ton of different information about how things bounce off the surface and then bounce off other surfaces in the world, and so on and so forth, right? And the problem that we have is that normally what we care about is we care about a continuous process of light being emitted from an emitter. So something that generates light, which is photons, right, coming out continuously. These photons are going to bounce around and then eventually get collected by a sink, which is our eye, right? So there's a photon generator and a photon, eliminator essentially, and the total flow of photons through the sink is what we are measuring. Now, the reason that this doesn't help us that much in terms of a fundamental structure is because although it lets us know one crucial thing about the problem, which is that for the surfaces in the world, the path along which you go to get from the emitter to the sink is what's important. And that is true. That's true for ours, that's true for here. Immediately subsequent to that, everything about the problems looks different. And here's why. First of all, like I already said, the number of photons emitted by an emitter and received by the sink are drastically higher in the real world than we will ever get to with the hardware we're talking about, right? They're talking about trillions, we're talking about, 10,000. So that scale alone is a problem. But beyond that, we have a second problem that really changes the nature of the solution. And that is, because we know we cannot do a good enough sampling of this process, we know we're going to do much lower level sampling of it, much lower quality. We need to be able to deal with it across frames. And in order to deal with it across frames, it means we have to store the information about what a surface's lighting characteristics were on the surface or at these sample points, right? And that's crucial because now we have to have a way of recording what sort of lighting is occurring at a point. And that is not something we ever had to deal with in the previous formulation. The previous formulation just says, I have a path through the world, therefore I know that a photon would have gone this route, and I can evaluate what each bounce would have done to this photon probabilistically done, right? Did this photon reach the eye or not, and what wavelength was it? That's all, right? But now we're introducing this additional concept, which is like light stored, some information about the lighting stored at the sample points. And one of the problems that we're running into right now in our lighting algorithm is we have no formal way of talking about that at all. We have not developed any sort of rigor to that measurement. It's just a completely made up floating point number called emit C0, right? And we have no idea what it means. No idea at all, right? So I think that's the first thing we have to tackle, is we need a formulation for stored light that means something. And even if that thing is basically identical to what we're already doing, just understanding it a little more deeply about what that number is supposed to represent, I think will help us as we try to improve our algorithm, because then at least we know what we're talking about, and we're not just fiddling with floating point numbers hoping that something goes our way, right? Which is a valid way to find an algorithm if you really don't know. Random search is totally fine. But obviously, if we can get better than random search, we would like to. There's no sense being random in your search for your algorithm if you can find some way of doing some math or doing some thinking to get you to carve off the space of possibilities into some narrower space so that that search can be more constrained and more successful more quickly, right? So pretty basic idea there. So we need a formulation for stored light that means something. And then the second thing we need is an understanding of emission, and I don't know what we want to call the sink side of things. Emission and, I guess, nullification, extinguishing. So basically, in our system currently, we don't distinguish between the light that the game told us was getting emitted on a frame, right? That's the emission values that are actually specified. Like we've got those little hopper snake dudes who are hopping around, and they've got little lights attached to them, right? We've got our white cube that well, it's not really a cube, it's more like a prism, our white box that we move around, and that emits light. And we've got the skylight, which we can turn on, which emits light as a dome. So those are three things that are emitting light right now. But all they do is just write into the emit C0 array, which is the same place that all of the surface stored light from previous frames that's bounced around, that's the same place that that goes. So right now, we don't even do any thinking about what it means to mix something that's emitting light continuously as a generator of light and something that's just storing the result of light that has bounced around. And again, that may be fine, meaning it may be fine to have those in the same array working the same way, but we need to understand that. What does that mean? Because one is measuring one quantity, one type of thing in nature, and one is measuring something different. In one case, with the actual emitters, we're measuring something that radiates photons itself, right? A lamp, the sun, whatever. It's something that has a actual physical reaction occurring inside it that is generating new photons. So photons do not have to come from anywhere. They are coming out of this thing with no need for anybody to do anything, right? The other elements, all the rest of the elements in emit C0, besides those ones that got set by actual emitters in the render push call, all the rest of those values are all talking about light that is transient, right? It's light that came from an emitter at some point in the past and is now sitting on this surface and can be bounced away. All right? Now there's a final thing that I'd like to include in this analysis, one more thing. So this is, let's call this number 1. We'll call this number 2. There's one more thing, and that is the difference between the render color and the emission. So one more thing that we don't really address is when we have light that's inbound on a surface, we are using a single value that will then be pushed to the renderer that colors that surface, right? So the surface itself has a reflection color. There's an inbound light color, and that inbound light color times the surface color is what we use to render the surface. Now, that result is the same result that we use to bounce the light around. So on any given frame, the thing that we draw on the screen is the same thing as what we're saying will be emitting light on the next frame. That seems reasonable, right? Because that's how light works. When we look at a surface, what we see is the light that's coming towards us from the surface. It's light that has been bounced off the surface. So the render color that the eye sees and the thing that other elements see when they go to take light from a surface, it makes sense that those would be the same, right? So that's not weird. You know, that's reasonable. But we have no rigor about that either, right? We don't even say what that value is stored as. Is that supposed to be flux? Is it supposed to be the number of photons passing that are inbound on this site as far as we know? Is it supposed to be the number of photons that we expect to leave the site? And so on and so forth. Right now, it's, I believe, the number, technically what we're doing is you know, the amount of photons inbound on the site, because we haven't multiplied it by the reflection color of the surface yet. We're just storing the inbound light. So I think that's the in radiance at that point, is what we're actually storing in no particular units, right? But just a value that's quantifying that, right? And so when we push that down, it seems reasonable, right? But we need to, again, make sure all of that understanding is clear, and that there isn't a difference that we need to respect there that has, ramifications for the way the lighting is transmitted or anything else like that, right? So we just want all of those in there, and I think out of these, these are the two that need to kind of get really worked on. This, like I said, I think we want to kind of just nail down, but it seems like we sort of addressed that early on, and we have not been too fast and loose with that. Like, we did actually correctly remember, like, okay, here's the light inbound on the surface, and then when we go to transmit that light or render that light, we multiply by the reflected color. That seems, plausible to a certain extent, right? Okay. All right. But, okay, so let me just point one thing out that I just thought of on point 3. The reason I think it's worth considering is because, for example, one of the things that we're having right now is we have a little bit too much, we have trouble keeping our light balance correct. And one of the things about number 3 is that, for example, when we are transmitting light between surfaces and we're taking the inbound light on one surface and we're translating it into inbound light on another surface, I don't know, for example, if we are correctly representing the power drain necessary on the outbound surface as compared to the inbound surface. We may be, for example, subtracting away the light multiplied by the reflection color, which would be wrong. There's a couple things like that, right? So it's just worth noting that, like, again, although we are sort of, this is more rigorous in the system than the other two. It was more thought through a little bit. It's still not thought through all the way, and it's probably not at the point where it needs to be in terms of our understanding. Even if the code is right, we need to, again, make sure that we're actually thinking about that everywhere that we need to be thinking about that. Okay. So that's how I want to think about that. Okay, so let's talk a little bit about what we're trying to accomplish here in light of these 3 things. So we have situations now where we've got this sort of thing occurring. We've got, P0 and P1. And the first thing is that really we can use, right now what we're using is unidirectional transport. Right? So what happens is we find from a sample point in the world, we find another sample point in the world, and right now we actually use more than one. So right now we're actually blending. So, if we've got another P2 here, and we happen to land, more in between the two, we'll average, right? So we're using a blend. But the important part is, when we do this hit, we only move light from here to here. So it's unidirectional because it only goes this way. Now, we could stick with unidirectional transport, and we may want to. The reason that we might want to stick with unidirectional transport is because it may end up being that if we need to do a decoupled version of this algorithm, it may be that unidirectional transport is easier to decouple into something that can be multi-threaded or, GPU'd or whatever. It's possible. I don't know. We haven't looked at it yet. Right? But if we assume temporarily that there isn't some ancillary performance benefit to unidirectional transport that we don't know about yet because it only exists in a structure of the routine that we haven't addressed. If we're just talking about the structure of our current routine, bidirectional transport would be much more efficient here. Why? Because what is the expensive part of our equation? Well, the expensive part of our equation is finding the path. right? The problem is not the few calculations that we have to do the light transport. The hard part is the fact that when we go to figure out what we hit, we have to look through like hundreds, even with the spatial hierarchy, hundreds of things to find out what that path actually was. And so finding the path is expensive. And rather than only using the path to transport light one way, what we really would rather do is use it to transport light both ways, right? Because if we do a bidirectional transport, where we basically say, oh, when we transfer information, let's take light from these and give it to this one. Let's also take light from this one and give it to these. And that way we can look at light equalization between two things, which again, very common in radiosity. It's not an unusual thing. So since we are basically a radiosity scheme at this point, seems like a reasonable thing to try, because that gets us twice the efficacy from our pathfinding, because now instead of having to wait for P1 to find the path back to P0, we can just use the fact that P0 found a path to P1 and know that P1 could have seen P0. If P0 can see P1, P1 can see P0. There's no difference in the sidedness of these paths. It's just whether a line connects them. So as soon as we find a path from one to the other, we also have a path from the other to the one. That's just a given in how ray tracing is structured, right? Either there was an obstacle blocking the line or there wasn't. So if we change to using bidirectional transport, I also think we would be able to get more leverage out of the same number of path finds, twice as much information there, which is great. So what I'd like to do is certainly explore that as a separate option, which is just to say we can start looking this as a bidirectional problem. I think we'll get more efficacy there. Okay. So let's start talking about this. A formulation for stored light that means something. So let's say I've got something that's emitting photons here. I've got a reflector. And I've got a collector here. And by the way, this is not me trying to teach you something. This is me literally trying to figure this out. So I'm not suggesting that I already know the answer. I'm just pontificating about it, just completely open-ended. So, if this is something that's emitting, I guess I should say collecting. I said emitting. So I have something that's sending photons this way, and I have something that's collecting photons over here, and I'm bouncing them out, right? Then the thing that I need to know for a particular surface here, right, is if I was going to take a frozen moment in time, right? So if I want to look at like an instant in time, what I could say is I could say something like, I want to know the photons per second, right, that are passing through this reflector. Because even though this reflector, like, even though there is no color, right, technically at this reflector, because color is something that only happens when we perceive it, we can still store the quantity that we care about for reconstructing this scene. So let's say we wanted to remember a single value that would let us get rid of this emitter and just remember the reflector and then properly calculate what happened at the collector, right? Well, photons per second is the thing that we could keep, right? If we know the photons per second that were inbound here and coming out this way, right? That were transiting this bounce, just this one bounce. The photons per second for that bounce would tell us exactly what we needed to know to figure out how many photons per second are getting collected at this collector, right? Now, this ignores the color, like I said, but you can imagine extending this pretty trivially to 3 colors, right? red, green, blue, by just storing the photons per second for each. So that's not that complicated. We can kind of just think of this as monochrome. So if we think of each of our reflectors as having a photons per second that's inbound and outbound, right? That is a sort of different understanding of it than what we're using now. What we're using right now is more like actual number of photons, in a sense, in that we keep them on the surface and then send them away. So we don't really have the notion of the photons per second that are transiting through. We sort of just have a notion of the number of photons that are sitting on this surface, right? And that's kind of confusing. The difference between those two things is subtle, but it could make a difference. So it's worth noting that the thing we actually care about, the value we actually care about, is an idea of how many photons per second are transiting through this particular surface. And we don't really have that in the current system, but we could imagine that it probably related to the number of photons that ended up stuck on this surface, but maybe it doesn't really. You know, who knows? All right. So, for example, suppose we were going to change the way we looked at this problem a little bit. Here is a way that photons per second versus photons would be important. Like I said, we are sampling, we're a shooting based radiosity because we can't afford to do anything else, which means we're just taking Monte Carlo samples, right? Actually, very much like the paper that was referenced yesterday, we're just taking Monte Carlo samples and then trying to reconstruct what the radiosity is after that. We're not doing a large linear system solve, which is one way you can do radiosity. We're not doing anything that would be considered a simultaneous solve. It's an iterative shooting scheme, right? The most sort of basic kind you can do because that's what we can afford to do at 60 frames a second over time. And we're trying to make that converge to something that would be a stable solution, right? And of course, converge to a stable solution is not even really what we want because lights are moving every frame and stuff like that. So we just want it to be something that becomes consistent over time if everything was stationary, right? Okay, so for example, let's suppose we have photons per second as an estimate on a particular reflector. And now we want to update the world. Well, you could imagine us shooting photons, right? Not photons per second, but actual photons from an emitter, looking at how many hit this surface and bounce out, and update our photons per second based on that number, right? So we have a quantity that's sort of saying how much generally bounces through the surface. Well, how much bounced through the surface this frame, right? How many went in here? So every time something hits a surface, we send it out. We send out all of it, right? We just bounce photons around like a photon tracer would. But then like a radiosity solver would, we then say, okay, let's try and figure out what that means for our stable photons per second, right? So again, you can imagine sort of thinking about this in two different ways. There's sort of the concept that we have a certain number of paths that we're evaluating, and then we're trying to update a value which is photons per second, which can be only loosely related to what the path says, right? The path is just one sample that gives us a hint about how the photons per second is probably changing. So given that, let's talk about what happens when we want to evaluate two surfaces. So let's expand on this concept. So let's suppose we were talking about photons per second everywhere. So an emitter also has a photons per second, and that photons per second value is constant, right? So we know that this emitter, you can't modify the number of photons per second it's putting out, because it will always put out the same number of photons per second. That's what makes it an emitter, right? So unlike the other elements in the system, and this is kind of an important piece of understanding, like I said, we're trying to get to this understanding by thinking through the problem about what we know about light. So if an emitter is putting out a certain number of photons per second, then it should never be modified, meaning that value that's in its emission quantity doesn't go down. It can't, right? Because an emitter outputs light all the time. It's not something that can be diminished. It's always going to have the same photons per second, right? So rather than thinking, and I think this is good, I like where this is going, rather than thinking about the system as an array of values and we put some quantity in one place and we let it flow to another and it goes out of there, almost like water. I don't like that as much as thinking about it in terms of photons per second. So the emitters are basically a separate array that's saying, here's where light is always coming from. These are constants. And then we have a secondary array, right, which is thresholded on that. So we're basically saying the secondary array, which actually computes the photons per second for everybody, those get cold copied in and hard set always to the same photons per second, right? And everybody else's photons per second are equalizing out and can be mushed around, right? That's a more coherent way to think about it for me, because it goes back to values we can actually put our finger on, right? Flooding photons into a value and letting them drain out creates this weird thing about what should that quanta be and how should we normalize it. Whereas photons per second is something I can put my finger on and say, it's constant for emitters, everybody else it equalizes out based on our samples, right? What we guess that it should be. Okay. So now we come to sort of the crux of this understanding that we need to determine. And that is, suppose we're not talking about emitters. We just have photons per second. So all of these are photons per second. And now we've got a situation where we've traced a path between two of them. So we know that, for example, if this is, sample 0, actually, let's just use A and B. So we know we have a point A and a point B, right? And B has a certain, we'll call this FB, we'll call this F of A. We know that there are certain amounts of photons per second passing through these points based on our previous estimate. Now, we don't know how to make that estimate, but we know this is an iterative algorithm, so we're just going to assume, for the purposes of determining how we do our updates, we're going to assume that we have determined some number of photons per second that are passing through these points, but that's all we know. Now, in one case, because in a sense this is inductive, right? It's saying we know what the first thing is. We know what F0 was. We don't know what F1 is. So we're trying to get the thing that takes us from F0 to F1. And we do know a startup case, which is an emitter. We know the photons per second at the emitter because we're specifying it. So it makes it an emitter. So we do know how we're going to get our first set of photons per second. So now the question is, if we assume that some people have photons per second, we just don't know who they are, how do we update other people based on that information? Okay. So if we know, right, that this has a certain amount of photons per second passing through it, and we know that this has a certain number of photons per second passing through it, and we know that they are connected, so they can send photons to each other, how can we update the photons per second in a way that starts to properly equalize our light? Right? So I think the first thing we want to recognize is that the photons per second is not a value that comes and goes. And I think this is where where sort of my basic idea before of how to compute the radiosity was just kind of wrong, was that I was doing it more based on quanta, which is just not a useful way of doing it. Again, photons per second, I think this makes a much clearer picture. Photons per second is not something that comes and goes. Photons per second is something that we need to use an estimate of what we think the photons per second should be based on what we've seen and what we were. So I think what we'd rather do is for every person that we're summing, we want to take every, photon per second path that we found, right? And average. So if we found a number of these paths for B, for the, on the next frame, the subsequent one is for every photons per second pass we found, we average those photons per second together, right? So we basically say, well, if I saw this guy, right? Let's say this is f of c. If I saw this guy, and this was a certain photons per second, and I saw this guy, and this was a certain photons per second, then obviously, and when I say average, I mean using the cosine influx, right? So we're going to weight based on angle, certainly. Averaging those together should give us the photons per second inbound at this point, right? It's not addition, it's an average. Why? Because we want to know the average photons per second passing through this point. It doesn't add them up as if they were quantities that shot at us individually. It's just an average of what's the light I can see. Well, the light I can see is an average of all of the photons per second of all of the surfaces that I can look out and perceive, right? And if we want to take that a step further in the future, we can have different surface qualities that actually react differently to different angles as well. But I don't know that we, in other words, not just cosine fall off, but actually have lobes of reflectance. I don't think we want to do that because I don't think we're shooting enough rays to really do much surface approximation in that way. But, you could see how you would extend this technique in that way. So I think we want to do for every path we find, we average the photons per second modulo the cosine term. And then we assume that our photons per second can only change at a particular rate. And this is to avoid the flicker, right? So again, we assume now, in addition, that, we blend with the previous frame. Based on a maximum change rate. So again, I think we're really close algorithmically to what we want, but we just need to change our thinking about it a little bit and change what our quantities mean. And I think once we change what our quantities mean to something a little more amenable to what we're doing, I think we're going to be okay. So mainly just changing to an average and then retaining that concept of a blend at the end. Okay. So that all makes really good sense to me. Why does that make good sense to me? Because that solves number 2 as well. Now we don't have to think about photons coming from and going to somewhere. Because all we're doing is thinking about the flux. We're just thinking about the amount of light passing through a surface. We are no longer thinking about an individual piece of light that goes. Now, we are thinking about that in terms of the path tracing, but we're just using those particles as tracers to figure out how to update the photons per second. We're not using them as if they were actual quanta of light that we're pushing around, right? It's very subtle. Smallest little difference, but sometimes the smallest difference can make all the difference, right? And then finally, this for number 3, I think we get the answer out of that as well, which is that once we know the photons per second, and again, we can keep through our path tracing and average light direction, that's all we need to hand to the renderer, the average light direction plus the photons per second of red, green, and blue channels. That should be enough for it to do the lighting computation that it needs to do at that point, right? So I think that's a fairly sane way of looking at the problem. And again, photons per second is an abstract idea. We don't have to actually measure photons per second because photons per second would be an astronomically high number. So we're talking about some scaled quantity that just relates to the photons per second. So say 1.0 is a million or a billion photons per second or something, right? We don't have to actually tie this quantity back to something physical in terms of its actual value. We're just trying to tie it to something physical in terms of its meaning. And that's crucial because that's the part that will allow us to do a good solution, right? The units are irrelevant in terms of their scale. They're not irrelevant in terms of their semantic quality. So understanding that this is a linear quality relating to photons per second, that's the important part. And it's the part that we weren't really talking about or thinking about before. Whereas whether it's actually photons per second or some other like billion photons per second or something, that part is not relevant because the scale is tunable by us based on the exposure value we want for the brightness of the scene and what we want our light values to mean. So that's just a separate part of the equation we can look at later. It doesn't matter for purposes of the lighting because the lighting is going to produce the same solutions regardless of what the scale of those values actually is. It's just the renderer's brightness that will change. So we need to, be aware of that in the second half of things, essentially. So I'm pretty happy with that. I'm pretty happy with that. Let's take a look at how this routine is going to change, because it's not going to change that much. And then I also want to go ahead today, if we have time, in addition to this change, well, I haven't even opened my command console yet. There we go. In addition to this change, I would like to go ahead and make the bidirectional version if we have time today, because I'm pretty sure that is just a smarter way to do it, because finding those paths is expensive, and so I think we want to, as much as possible, unless there ends up being a really strong reason why we are unable to do so, I would like to make it so that we can reuse each path that we find. Okay. So let's take a look at how we're doing this here. So inside, when we open up our lighting test here, what we've got is we've got our emit C0 and our emit C1 values. And what I'd like to do is now make these values mean something a little bit different, perhaps, than they were before. So what I'm going to do here is just going to play around with it a little bit just to see if I can set up a situation that makes a little bit more sense to me in terms of how to structure the routine, and we'll go through it step by step. So we know we've got two things here. We know we've got emit C0, and we know we've got emit C1. So what I'd like to do here is I'd like to move to considering emit C0 as the actual stated emission values of the light at a particular time. And emit C1, well, okay. You know what? I may be getting ahead of myself here. Let me not say that quite yet. So we know that the emitters are never going to change their emission values, right? So they're always going to be exactly what, whatever they were. We know that it's only the average value that's going, the new value for the next time that's going to be changed. So I think what we want to do here is we want to, rather than do this as a plus, what we want to do is see whether this is an emitter or not, and update it that way, right? Because if it's an emitter, it's going to cold set the photon value. And if it's not, then it's not. Now, there's two ways we can look at this. One is that we can support things that are both emitters and reflectors. I don't know whether we want to do that or not. We may want to. And if we want to, then we need a good way of understanding that that's what's going on. Which means we're going to need the... we almost need like a third array for that, I think. Because I don't really see a lot of ways around it. Let me explain what I mean by this. Okay. So let's suppose I have a surface that's an emitter. But it's also a reflector. So we want to be able to compute both. What's an example? Well, let's suppose this thing is emitting red light, but it's actually a gray surface otherwise, right? So if green light came in, we would expect green light to come out, proportional to how much went through. That would be an emitter reflector. Now, why do we care about this? It may seem like a thing to not really care about. Well, let's suppose we want things in the world that are not lit that become lit. And we want that light to fade in. Well, if they're not lit originally, they need to be reflectors in order for you to see them at all. Otherwise, they'd just be black, right? But now, what's going to happen is as the light starts to fade in, the instant you get any emission there at all, if you can only be an emitter or a reflector, it will suddenly snap to black, then gradually become bright in red and lose all of its previous color. That will be a nasty visual artifact. So if we want to be able to transition between an emitter and a reflector nice and smooth, even if we don't care about anything else, just that effect, I think we want to do both. So the thing that I'm concerned about here is that if you look at what happens with emission reflection, on the subsequent frames, I need to be able to know that I'm not adding in like this additional emission that's coming from the user. I'm just saying that this is how much has to be emitted at a minimum, right? So I need to know the difference between the emitted light and the reflected light, because if I don't keep those quantities separate, I don't know on the subsequent frame how to interpret the emission value coming from the user. Because I don't know how much light I was trying to say I was taking above and beyond that previous emission value. So I realize that's a little confusing. I just don't know another way to deal with it at the moment, right? So what I'd like to do is maybe just expand this a little bit, and we can collapse it down later. We can, in the future, try to do something where we, handle this in a way that doesn't require extra storage or something as we optimize. But just right now, I'm just not sure how to do it any other way. So I want to be explicit while we get this routine working the way we want, and then later I can optimize it if I think I understand a good way to do that, right? So I'm not going to call these emit C0, emit C1, or anything like that. I'm going to actually start to be sort of more explicit about this. This is the emission array. So that's how much light something is giving out, let's say. Well, okay, let me start with things I know. So this is my photons per second, right? Like we just talked about. And so this will be the starting for, this is like accumulated PPS. Is that? So we know we need an initial photons per second and an accumulated photons per second. And we also then need some emission photons per second, which we will add into the accumulated photons per second to produce the final value, right? I think that's essentially what we want to talk about here, I think. Not entirely sure, but You know what? We may not need to track that, though. I think we may only need to track these two, and then we can just add in at the end by doing this a second time. I'm going to keep it as a separate array for now, but I think we can maybe get away without it. Okay. Yeah. Okay. All right. So let's go ahead and move forward with this. So let's suppose that we have the let's suppose that we have these values initialized the way we were doing it before. So we have the initial photons per second. And we want the initial photons per second to be the old value plus any emission that was going to come through. Right? And again, these are, we don't have a specific unit for this, so we're just going to use whatever the old units were, and that's fine. Right? We're going to set the initial photons per second this way. And the average direction to light is a value that we're summing up and averaging. So this was actually, this may have been a big source of our flicker, actually. I didn't, for some reason, address this. I didn't think about it when we fixed the fact that we were erroneously computing it before, and that was a source of flicker. You know, another source of flicker is just the fact that we are not weighting the average of these two things to force the direction to bend slowly over time. So the other thing that we want to do is we want to have a stable update coefficient here, right? So we want to have something that effectively says, all right, what is our sort of update per frame, or what is our update rate, right? So our update sort of blend coefficient here, let's suppose that it's going to be something like 0.2f, so it takes, 5 frames before we update our lighting or something like that, right? Well, if that's, and maybe that's too high, well, no, this is a tunable coefficient, we have no idea. Also, we are doing this now, so let's get rid of that comment. So if that's the case, then what that means is that the direction here actually wants to be multiplied by that inverse, right? So what we want to do is say 1.0 over the t update is what we want to multiply this direction by so that it's weighted much more strongly than the average direction to light that we're taking from everybody else, right? That way, when we add in all of the other light samples that we get, we can minimize them that way. Now, it's probably the case that we would rather, since we don't know how many pass samples we're going to take, it's probably the case that we would like to normalize those separately and then blend in. So another way to look at this might be that we really should clear this value and then blend it afterwards, right? So it could be that this should just be set this way. And then in the end, when we go through, we do actually want to do that update. And now this stuff where we do the blending, I think we should be fine to just always blend. It will mean that at first things get a little slow. Yeah, maybe we want to just use it right out of the gate. So I guess this is fine. I guess the way we're doing this here is fine. So this t update value here is what we're going to use. So when we come through here and we do our update, we do want to do exactly this, meaning we want to average our light direction with the previous direction. That's an important step, and I think we were getting flicker from that before, unfortunately. So we probably should have taken care of that previously, but unfortunately we just didn't. Right? So now we've got that part. And what we need to do now is we need to take a look at our other values here and write those back properly. Now, I would like it if we could do this a little bit more sanely here. It would be nice if these were always, if these values always kind of could just be done in one loop. I mean, I wish we could always do this and we just stuff the values. The problem is, since we're doing them over a set of points like this, I'm not sure how valid that actually is, but you know, since we don't care about the speed of this loop yet, it's not part of our slowness really. What I could do here is actually do the if inside. So I could actually do an if valid here. And deal with that and make it so that we actually can simplify this down. All right, so what I mean by this is inside here where we're doing our update per point, instead of going directly with the box storage value, we're going to grab those out. That way they can be set to default values in any other circumstance, right? Okay. So we know we have an accumulated PPS and an emission PPS. And what we want to do is we want to add those two together for the final value that gets written back, right? I'm sorry, that's not true. What we want to do is only write back the accumulated PPS, because that's the part that we're actually going to store from last time. Yeah. When we output the lighting to the actual lighting system, then we use accumulated plus emission PPS, which is what happens in output lighting points. Sorry about that. Okay. So what we want to store here is we want to store our accumulated PPS, or our last PPS, right? And last direction. So these two values are going to be equal to the ones we're actually going to use. So this is going to be, here we've got our accumulated PPS, and our direction. And what we're going to do is we're going to assume that those equal whatever the ones we're going to blend to are. And then when we come in here to actually store these values, what we're going to do is we're going to do the blend regardless in all circumstances, but we're just going to blend it with itself in the case where the thing wasn't valid. And that's just me simplifying this routine because I didn't like having to pass there. Again, that's something we might do when we're looking at performance, but right now we know this isn't a slow part of the routine, so we can afford to just do it in a way that's cleaner and easier for us to debug. Okay. I shouldn't say cleaner. It's not really about cleanliness. It's about simplicity. So if we come through here and we're going to set the box storage local index.emit, that's essentially the last PPS value here. So that's going to, I don't think we need to actually update emit C0 in this way necessarily here. Because this value is not what we're writing. Well, okay, so we do want to, because we need it to be picked up from somewhere, so I guess that's fine. So we know that this is this accumulated PPS, and in fact, I suppose we can sort of make this a pointer as well if we want to, but let's go ahead and do this a little bit more explicitly here. So if I grab out my accumulated PPS here, and my average vector to light, those are the ones that we computed on this frame. And what I'm going to do is I'm going to update them here the way they should be. So we know this one should be normalized, the direction, because it was an average here. We know this one needs to be averaged over the number of samples that were taken. And right now we don't know how many samples were taken. So that's an additional piece of information we're going to have to take. Right? So what we want to do here is take the accumulated weight, and multiply it. Now that accumulated weight value might be 0 in the case where we have no samples, and that's fine. That just means that we didn't accumulate any photons per second passing through this point. That's going to happen for surfaces in the world, and that's fine. And then we're going to normalize our direction to the light because we know that we just shoved a bunch of things in there and we want the average. We don't care what the weight was because we have to normalize it to a unit direction anyway, right? Now, it may be that in the future we want to not do that. We want to use the weighting of it and persist that forward so that we know that when we take more samples on a frame that we want to use more of it and so on. I'm gonna go ahead and say let's not do that yet because that gets into a little bit more complicated, like trying to see what we should do sampling wise here, and that's a little bit much. Okay, so if we have last PPS here and last direction, then initialized to these two values, we will grab them out in the case where we know that the previous values were okay. And then what we want to do is we want to do a write back here that will produce the final values that we need, right? So we don't need to remember the average direction to, well, we do. Again, this is just for the output routine. If we did output lighting points at the same time, not output lighting points, sorry. If we did output lighting textures at the same time, we wouldn't have to do that. Kind of makes me think that that should be in here. But again, we'll deal with it for now because it's not really that important. Okay, so the average direction to light and the local index direction that we're writing back, those are going to be, this one's going to normalize just the lerp between the old direction and the new direction. And that T update there, again, is low because we want to take at least 10 frames, we're saying, to shift lighting over, so because we just don't think our samplings would be good enough to update it any faster than that without too much flicker. So here's that direction, average direction to light update. This will update both of those. And then finally, we've got our box storage last PPS value. And again, that's going to look exactly the same. So that's just going to be a lerp between the previous value and the new value. So that will just slowly move our expected photons per second through the surface and our expected direction to the light source slowly over time towards what we are seeing as the current accumulated value. And off we go, right? Now, again, I'm not sure this is really the best way to sum these things, because if you imagine what's happening here, it's not clear. Well, you know, yeah, I'm not going to go too much into it. Point being, we have a set of samples. We have samples from last frame, samples from this frame, samples from next frame, whatever. I'm not sure here that we're weighting all of those samples as well as we could be for our results here. So take that with a grain of salt, I guess is what I would say. Because it is a little confusing to really know what's supposed to be happening there, right? So the other thing that I'm going to do here is, again, I'm going to set up the emission values to be something that's more understandable here. So the emission PPS, I'm going to set for this light index as so. And as you can see here, so what I'm trying to do is say, all right, I want to remember what the emission value was for this, because I know that my initial PPS and my accumulated PPS are not representative of that. The initial PPS stores whatever amount of emission particles per second are supposed to happen, plus whatever the emitted ones were. And I know my accumulated is going to be something that's based on all of the averaging that's happening. And so what I want to do here is remember that so that later when we come through here to output the actual value, I want the color of the surface to be the accumulated photons per second plus the emission photons per second, because that is actually coming at the eye as well, right? Those emitters are coming directly out of the surface in addition to anything that bounced off the surface. So, then if we say that we have that information output, I think we're good here. This same value is going to be used up here, like so. And I think that's all we really care about there. All right. So again, the only reason for storing it there is because we don't want to recreate it, but we can recreate it. So we don't really need this. You know, this is... So we're just doing that to try and make sure that there's less bugs. Like, I don't want to compute the lighting in two different places if we don't have to. If we can just store an array, then it's fine, and so on and so forth, right? Okay. So then when we go to compute light propagation, now we've got to update this routine to be more reasonable. Now, the nice part here is that the blend amount and the ray count and the power and all this stuff, I think, goes away now. I think we just don't care about any of that. It doesn't matter. So it can just be deleted. All we need to know is how many samples we want to take, which is the ray count, and that should be sufficient for our purposes. These values are all actually V3s here. And we don't need total added and removed. We don't need accumulate sample to return anything to us because it's not about that anymore. And we certainly don't need any of this either. So let's go through this now and update it to do the thing that we want it to do. There's no source emit or dest emit anymore. Those aren't things. Neither is this. So what we're going to do now, I'm going to stick with unidirectional for now, but again, I'm going to say that we want this transfer to be bidirectional in the future. So off we go. We come through here. We sample the hemisphere. We find a path that says that these 2 points can see each other. And then what we want to do is we want to go ahead and record samples for these points that tell us how much... that tell us how the photons per second should be perceived here. Okay. So accumulate sample is still, I think, our friend. The angular falloff still wants to be there. The light power is not relevant anymore. So that goes away, I believe. So it is strictly the angular falloff in question. The weight is just the angular falloff times that light color. And I think this is what we're talking about here. Right? So we want to sum up the value here. We want to sum up these two values. And so actually when we're looking at what we're summing into, all of this, I think we should just pass the sample index. Right, because this is going to be, the surface normal is going to be just the points normal. Right, so I think we can kind of not do it quite so. I think we can make this much more concise, I guess is what I'll say. So the surface normal, if we just pass instead the lighting solution here, then what we can say is the solution points for the dest sample index is the surface normal that we're talking about here. The angular fall off is going to be the surface normal and the normal to light, right? And the normal to light will still get passed in. The weight is the length of that light color there, and that's good. And then all of these are going to be pulled off of the solution, right? So the solution accumulated weight is going to be plus equal something. The solution accumulated PPS is going to be plus equal this. And the solution average direction to light is going to come through there as well. So this is really going to be computed here. We can just use that since that distributes. Those are the same answer, right? So the weight times the normal to light you can just get from the length of the color sample there. The accumulated part per second is just the sample color. And so that's the sample that we're taking for photons per second. And so now the question is just what is the accumulated weight? Well, if we just want to average all of our samples together, it would just be 1. If we want to use the angular fall off to say that some samples are more important than others, or something like this, then we would set it to something else. I'm going to set it to 1 for now. And we can weight those differently if we want to in the future. Okay, so we don't need this. We just need that. So we just pass the destination sample index. We pull all the values off of that. And then we just need to pass the surface, not the surface in, just the light color and the normal to light. And that's our accumulate sample. So that's how we would do that. I'm not sure if we want to pass in an additional scalar here because it could be optimized potentially. That way we'll see in a second. But looks pretty good. So let's go ahead and move accumulate sample down here into what we're actually doing. So we now know the sample that we're accumulating is this one. And so we want to pass the solution, the death sample index, and then we want the light color, which is, you know, this mythical emit C value. And I'm going to change that to basically the transfer PPS. That's like how much we're trying to give it. And then the normal to the light is going to be the sample direction. That one we know exactly. So that's how we will accumulate our sample. This is not a thing at the moment, although we may want to do that as a measure in the future, I suppose, of what the total light is. But let's see what's going on here. Source sum, dest sum. I think all we really have to do is some clearing here. So before we start, the sample stuff has to get cleared. So emission initial, so in here we need solution accumulated PPS needs to be set to nothing, and in addition to accumulated PPS being set to nothing, accumulated weight needs to be set as well. All right. So let's go ahead and update this routine here. When we do this, this is going to be our transfer PPS here. I guess we call this see, we want to change this to be bidirectional eventually, so it shouldn't really be transfer PPS, but we'll call it that temporarily. So when we come through here, right, we're going to sum up the total weight. That doesn't change because it's just producing a weighting value for each of these points. And then when we come through here and we loop through these, we're basically going to say this is the source emit C, right, is what we're grabbing from. That's now going to be our solution, not accumulated. Initial PPS, so that's the previous frames, photons per second, plus the emission. So that initial PPS that comes in, that's how much, this doesn't happen anymore, that's how much we're talking about here. And so the transfer PPS is either the moon color or I think it's this contrib C here, right? That weighted contribution of how much of that has, you know, it's been equaled out. Now the other thing we can do here, so actually, I guess now that I think about it, I'm looking at this to-do that says, is there any way we can get rid of the second loop? And the answer is, isn't there? It seems like there is. Because if we look at what's happening here, we're summing up a total weight value. And that weight value is going to divide our contribution, right? But we could instead just multiply by the raw weight value, whatever this value is here, right? And then multiply the entire thing by the inverse total weight later because it's a constant. So what we should be able to do here is say that the transfer PPS gets summed directly right? I mean, I don't see why not. If I just take the weight value here, and I say sum the values multiplied by the weighting value and sum the weight, when I'm done, I will have the inverse, right? And I can just take the transfer PPS and multiply it by the inverse total weight, and I'm done. Right? I mean, I don't see any reason why I can't do that. Maybe I'm missing something. But so it does seem like, I don't know why I thought I needed 2 loops. I guess I was just kind of out to lunch, or maybe I'm missing something there, but that certainly seems fine. I don't know that we need that at all anymore. And this is missing a parentheses. All right. So now we've got a bunch of debugging to do and like, you know, validating kind of what I just did, because it's sort of, we made a bunch of changes and we need to now like step through them and get them, you know, I put in what we said on the blackboard, just my first pass at how to make that work, but it's not going to be correct, right? As you can see. So we have to now like actually go make this, you know, A, debug it, make sure we don't have any weird bugs in here, which we probably do. And then B, we need to like turn the dial and make sure that we've got all the weird stuff out of it, right? Good news is obviously there's no frame rate issues here, so, you know, we're pretty much okay in terms of perf, I think. So it's really just going ahead and getting this to be computing the thing that I wanted to compute. All right. So I'm going to go ahead and turn off optimization, and we're going to step through this and start to make, you know, try to make sure that everything is working correctly. There we go. All right, so I'm going to come through here, and first thing I just want to look at is what's happening to my solution buffer. So this is where all of the operations take place. So obviously I want to make sure that these things are all set to something reasonable, right? So here we have set P1. And so we don't expect there to be any change there. The points are what the points are. But all of this stuff is different. So let's see what our initial PPS is. This should all be 0. Basically, there's none from previous frames. And so only just a few places where there's emitters should we see anything. Same is true with accumulated weight. That should all be 0, and it is. Same with accumulated PPS. That should be 0, right? And that is getting set there, which is good. And same with emission PPS, that should be set to 0 everywhere other than where the emission is occurring, right? So I think that should be pretty good. You know, I imagine that if we look at this, right, if we look at emission, there should just be like some little place where the emission is set to something. Of course, it's hard to find here. Should probably be setting this to the smaller number so we can have a better chance of actually finding the people who are emitting. I'm going to go ahead and just make one. And then I'm going to look at the emission array. I don't know how many points we have, though. 1849. So there we go. So here's a bunch of 1.5 emitters. I don't know how we got emission values of 1.5. That's not supposed to be. It's supposed to be 0 to 1. Great work, guys. You crushed it. I'm going to go, you know what? I'm going to go ahead and say that that's just not allowed, and we're going to fix everywhere that is doing that. because I don't know how... Oh! No. False alarm. That's post-multiply. So we're all fine. Totally fine. Everyone relax. All right, so we know our emitter is set here. If we look at how many of these are set to 1.5, I'm assuming that's for a snake, right? Should be one more at the end for our box, and all the rest should be zeros. There we go. All right, so that's exactly what we should expect, so that's good. Average direction to light should all be zeros, and is. And so off we go. Now we're going to do our compute light propagation function. We're going to come through here, and let's just take a brief look at how this is working as well. And we also got to check the output part. So we read out a point, and we try to find someone to transfer with. In this case, we did. We come through here, and we compute a total weighting value, which is based on the... I should also be looking at both of these at the same time. Transfer PPS, total weight. And probably, since this is our first frame, probably whatever it hit has no light on it anyway. So I'm guessing transfer, yeah, it is a 0. So total weight this is the total weight. It's going to divide out something that was already 0, so we'll just get 0 and no one cares. We'll then go into the sample accumulation. So we need the sample direction, that's where we're going to get the light. We have the transfer value, which is nothing. We have the sample point index and the solution. We come through here and we say, all right, the surface normal is going to be whatever the destination sample's index normal was, and that's exactly what we would expect, right? Totally fine. We've got the angular fall off, which is the normal to the light surface end, so there's our fall off factor. We've got our sample color now, that's how much we're actually going to add in here for the particles per second that are being added flux-wise. Again, it's nothing. The weight is also nothing for changing the average direction to light, so the average direction to light will not change based on this value. We have the accumulated weight, which again is just going to go up by 1. So it should just be 1, right? And off we go. Now, the accumulated weight value in this case, I guess accumulated weight will always be the ray count at the moment. So in theory, because we always count like the moonlight as the thing you hit, you can't hit nothing. We can actually get rid of that accumulated weight value. In the future, we can make accumulated weight just be a constant, right? It doesn't need to be, it can just be the number of samples that we take per point. Unless we adjust that value in an unpredictable way, we could just get rid of it. Because we know it's just ray count, and ray count could just be a constant. So again, we come through, here's another example where we have the moon color coming in. So the moon color now has a very specific transfer value. We're going to come in here, look at the angular fall off. The angular fall off is actually pretty high in this case. Why is it high? Well, the normal to light is very pointy compared to the normal, right? So the normal is pointing directly to the left, perfectly left. But the light value is more upward than that. So we're going to go ahead and get some transfer, but it's not going to be a lot of transfer. Okay. So that looks fine, right? That's basically what we wanted. Now there's some things in here that we want to do. And in fact, I'll add one more comment, a thing that I want to do just so I don't forget. Probably something to make our sampling more uniform than it is right now would help us. So we probably want a stratified sampling scheme. We'll talk about what that is later, but it's just something that makes sure that we don't sample in a very biased way due to randomness on a particular frame. It's a way of sort of making your random numbers less random to improve things. Anyway, so when we do all those accumulations. That seems pretty... Uh-oh. Oops. There we go. So at the end, then, we need to go look at the output step, the output phase. So let's go ahead and do that. So we assume that we did our light propagation now. Now we're going to grab the... Here we go. Look count 24. So now we... Oh. That's just a typo. Well, that's very bad. No wonder we weren't getting anything sensible at first. That's a pretty big initial bug. That's not supposed to be there. Valid is only there to see whether or not the original values were usable. So I don't know what's going on there. Yeah, that was just dumb. Yeah, that was just straight up dumb. Furthermore, this valid really should be done per time at this point, and I think we should just go ahead and do that, because again, we're going to have to figure out how we want to do that valid bit a little bit later, but I'm just going to go ahead and do it here. All right. Let's take a look at what the results are now that we've got rid of that stupidity there. So kind of ridiculous, actually. So still kind of a little bit nuts. So let's go ahead and step through this and see what's going on here. So these also need to get clamped, which I didn't do, so we should probably also do that, but I'm going to skip that for the moment. Although, well, you know what? No, I'm not. I'm going to do that right now, so I don't forget. You know what? No, I'm not. I lied. Because they get clamped in the shader, I believe. Am I wrong about that? So here in the ZBias program, I would expect to see the light values getting clamped. No, so they don't get clamped. So they probably should get clamped in the shader rather than not. So I think I'm just going to go ahead and say that they're going to get clamped in the shader. So in here, whenever stuff happens and we end up taking whatever the surface reflectance is, I'm then going to go ahead and clamp that. So I'm just going to make sure that that value can exceed 1 and it won't cause weird color overflow artifacts, right? Which may have been why the whole thing turned black before, I'm not sure. No, it's not. Must have just overflowed in some other weird way. All right, so I'm just going to leave that in there because I want to make sure that that's something that, yeah, can overflow if it wants to. All right. So let's go ahead and check this out now that it's actually going to enter the part of the loop that we care about there. So we're going to go ahead and take for any particular point here, we're going to use the accumulated PPS value. There's how much light it thought it received. Here's the direction it thought it was coming from. And it's going to go ahead and so on the first frame, oh, that's garbage as well. Not doing great on the mind slips today. So I want to use the last direction here to do the valid check, right? So this actually should be something more like that. So yeah. That looks more reasonable to me. And I also think there's another thing we could do here, which is if we don't get a valid normal, we could set the normal to something else as well. I'm going to ignore that for now. All right. So that's a little bit better, right? So, okay, so now let's step through here and look at what's going on. So when we check the valid value, it should be false on the first frame and is. So now it's going to set the emit value, which is the stored value from the previous frame that we use. It's going to set that equal to the accumulated particles, accumulated photons per second. Oh, and this is also backwards. Wow, there's just a lot of bugs today. A lot of stupid bugs. So yeah, don't know what was going on there, but obviously when you want to normalize something, you don't multiply by the weight, you multiply by the inverse of the weight. So that was multiplying it by 4 every time. No wonder everything was instantly perfectly bright. So I'm going to go ahead and say that the inverse weight is 0, and then I'm going to say if the accumulated weight and again, we don't really need to do this because the inverse weight's going to be constant in the future, I think, if everybody gets the same number of rays cast. But if we switch to bidirectional, that won't be true anymore. So I'm just going to keep it this way. We won't need to do this if 0 check because there's no way you'll ever get 0 samples, but you could get more than the average number of samples as well. So I'm just going to do the full thing for now. But in the future, we will simplify this a little bit. So now I think about it, yeah, this is... So at that point, we should be okay. The accumulated weight, the accumulated weight is greater than 0, then we do the divide. Assuming that's the case, we then multiply out the inverse weight. That gets us the accumulated PPS that we want. Let's step back in here because I've made so many mistakes in here now. I want to really check it out. That's the correct weight, 1/4, right? So now we get an accumulated PPS and a direction value out of it. The last PPS and last direction values are going to be set to those. We're going to have a not a valid, so we're going to blend between them, and that's what we get here. The T update looks right. Last direction and direction should be the same. And last PPS and PPS should also be the same. I don't know why it's not hover valuing those. Okay. So I think That's about right. In this case here, I will say that I think our moonlight needs to be significantly less bright as compared to our individual spotlight. If we want to see anything, I'm going to go ahead and change the moonlight value there. Should just generally do these as V3 so I can multiply them. Yeah. So how bright is that debug light as well? So that's 1.0F. So that should be... So something's a little off here because that should be significantly brighter. I guess it's because it's very unlikely that you'll hit it is the problem. Because that should have been significantly brighter than the moonlight already, and the fact that it's not is a little concerning. So we probably still have more work to do here. Also, I think that flicker is way too fast right now, so I think we're also, our smoothing is not correct. So I think we got some work to do here. All right. All right, so let's think about this a little bit more. Let's try to, let me do a few things here. So I want to test a few things now. The first thing I want to do is I want to do the standard test we were doing before where we don't update the average direction to light. So I want to set here D is always going to be equal to solution points, point index, surface normal. So I don't want to see anything that has to do with the average direction of the light. That's just going to get set. So we can just see the difference in emission value, right? And so what you can see here, if we're looking at the difference in emission value, also that's not in optimized mode? Wow, okay. I guess when you use a small scene, it's very fast. Yeah, that's like 60 frames a second when you use a small scene. Which is kind of cool, I guess. Interesting. So again, I think we've got bugs here. I don't know for sure, but I'm just trying to now isolate them out. So my suspicion here is that this looks like too much variance, but I'm not sure. Okay, so if I smooth it out considerably more than that, it does dampen it quite a bit. But it still flickers quite a bit more than I think it should. That's a 100 frame smoothing. I really should not be able to be seeing that like this, I don't think. So that to me seems like we've still got That to me seems like this lerp is not working properly for whatever reason. Again, because that means it should take 100 frames to change the light from one value to another, right? To between two different ones, and so they can only move by like a very small amount per frame, I would think. Now maybe we really do have that much noise in the system, but it seems a little unlikely. Hard to say. But so if we take a look at what's happening here, just want to make sure we're really doing it. So the accumulated photons per second value that we're putting in there is a lerp between whatever the last one was and this one. However, if the valid value, I guess... So I guess it could be if that valid value was turning on and off, that would do it. So I guess the other thing we can do is force that valid value to always be true again and just see if that is an additional source of noise there. Does not appear to be. So even at such a small blend rate, that flicker persists. Let's see if we drop it even lower. So I guess the fact that I can drop it low enough to... I can eventually drop it low enough to the point where you don't see the flicker suggests that the blending is working okay. So maybe that's all right. Maybe that's all right. So let's set it to something reasonably low. And I'm going to put a note in here. Go. And so the next thing I'm going to do is I'm going to try casting a few more arrays as well. So our array count's pretty low right now. And so the fact that more rays also seems to reduce it does suggest that it is just variance in our sampling as well. So that also seems good. So I guess now my main concern is I'd like to address the brightness level, because the brightness levels seem a little odd to me at the moment. And I'm not sure why that is. So I'd like to get a better handle on that going forward. Supposing we set the max light emission to something high, so let's say it was 50, we should get a much brighter scene, right? And we do. So let's set it to 25. There we go. So I'm okay with that so far. So I'm going to set this down to something more reasonable. And I think now we're starting to get... I'm starting to get into a position where I feel like we can converge here. I think now what we have to do is try to get our samples more stable. But I'm feeling pretty good about this, right? Our lighting values seem to converge much nicer now. And they don't go off the charts or do weird things anymore. And if we change this to bidirectional, that'll get us twice the samples sort of for free, which would be great, right? It means that, you know, for 16 samples, we're really getting 32 samples, and that's nice. So I think this is good. I'm pretty happy with that. Because we just got to get our noise down a little bit. And I think also, you know, putting in a real, I don't know what our current, like, we don't even have a real random number generator in there, right? So we should probably also take a look at that and do sampling that makes more sense, right? Okay, let's go ahead and go to the Q&A. Yeah, I'm pretty happy with how that is, actually. I don't even know if we just were doing this multi-threaded, we'd get a lot more rays. And we might just be fine. Like, we may actually be at the point where this is just going to work without reducing the noise much at all, to be honest. You know what I'm saying to you? Because if you imagine this were running at 60 frames a second, which we easily could do this many if we just multi-threaded it even on the CPU, forget GPU, I think we'd be in reasonable shape. We should improve our spatial hierarchy a little as well, as a separate issue. So the rest go, is that color banding I see? I hope that's just from being on stream. No, I think that's probably actual color banding you see. We have not turned on like any dithering, I don't think, on the GPU. And we may need, well, okay, I don't see the color banding. Yes, I do. So right in there you can see some color banding, and I assume that that is just from the fact that we are not getting like good dithering. We need to like set up some things on the GPU better to get dithering in there, because I can definitely see it in here, right? And I don't think there's any dithering going on in there. I mean, I can actually check for you. So if I open up like Paint or something, or GIMP, do you have GIMP on here? Yeah. Okay, didn't want to do that. So I guess I don't have GIMP on here. Who knows? So if we take a look at, you know, somewhere where there was more banding, it's kind of hard to see when the image isn't moving, but so there's no dither. There's definitely no dither. So what we probably need to do is we probably need to set up dither in the hardware to get rid of the color banding. That's not just a stream artifact. It may look worse because of the stream, but I can see it. It is there. So that's just a question of we've got to get dithered output. Check Zero. What do you think of game development frameworks like Unity? Do you think an AAA game can be made using it? It depends what you mean by AAA. Like, obviously, like, if you don't consider Unity, but you said, the Unreal Engine. Obviously, that was because Gears of War, right, is a AAA game, and that's made in the Unreal Engine. So I think Unity may be a bit of a stretch these days. I don't really know if Unity is quite there yet in terms of really AAA. Like if you want to make Assassin's Creed or something, I don't know that it's going to happen in Unity. But the Unreal Engine has definitely been used to ship AAA games before, and that is a available framework. You probably can't ship something that's too different from Gears of War, right? Because the engine is set up to do a particular thing, and so you need to be doing that thing. But at least one of the engines out there has been used to make a AAA game, and so that it is possible to make at least a certain type of AAA game with it. Unity, I've never seen a AAA game made in Unity. Maybe there is one, but I don't know what it is. Why sampling arrays can't be evenly distributed to eliminate the flickering wouldn't be fine with the phrase. The problem is that, yes, first of all, I think we will be able to do much better than we're doing right now. The problem with it is that you don't know what evenly distributed means. So let's suppose you've got a situation like this, where here is a bright light here and there's no light here, right? Or more to the point, let's suppose you've got a bright light here, but there's something in the way, and then we've got a situation here. Well, what you need to know is how much of the light source is occluded by this blocker. And the only way to know that is to find where these points are, right? And so the way that we do that, because this is such a complicated problem when you have a full 3D world geometry you're trying to analyze, is to just shoot a bunch of these rays and look at the percentage that hit the light source. Well, that's always going to be wrong. Always, right? And how wrong it is just depends on how many rays you shoot. So when you're talking about shooting so few rays, like if we can only afford to do 16 or 32 rays or something, right, per sample point, you're just not covering enough of the hemisphere to really get accurate percentages, and that's where your noise comes from, because every different frame, you're getting different percentages back. I've been watching a fair bit of the backlog. You seem to return values and functions via parameter pointers, even when you're not returning anything else, i.e. void func int arg int star return instead of int func int arg. Is there any particular reason behind this? I can't imagine it maybe stops the API. Can you give an example? Because not really. Most of the time we do return the value if we can return the value, right? Pretty much everywhere, that's how we do it. So the times when we have to take an input, it's when it's going to be something that's expensive to return, and we don't want to do that, or when we needed multiple things, right? So most of the time, we just take inputs and return the output, right? So I don't think that's an accurate statement, actually. This is what I'd say. Long Boolean. Are there any light effects that you can think of where assuming bidirectional ray sampling would give janky results? Maybe subsurface scattering? No, so bidirectional is always correct, no matter what the case is. You can always do it correctly. The question is just, what are you actually going to do with the bidirectional evaluation? Photons can always travel like the reverse, right? So I don't think there's any case where they couldn't. But I don't know. There may be something in particle physics that says that some certain case cannot be reversible, but I don't even know about that, because I've definitely heard things from quantum people that's like, well, we don't yet know whether time always goes forwards, right? Or stuff like that. Meaning like you could imagine a photon doing the exact opposite of what it did. So as far as I know, at least in lighting that we know about, in terms of computer graphics, I don't think there is such a thing as a forward path a photon can take that a photon going the reverse couldn't also take. Now, remember, the probabilities are drastically different. And that's why I say, it's a different computation. So the chance that a photon will take the reverse path and the chance that the photon take the forward path are completely different. That is true. But the fact that they could have taken the path, I think, is always the case. It's just a different probability. But you're accounting for that when you do your summation, usually, you know. Big Mofo 1 says, but if the rays are the same across frames, the flickering would only happen around moving objects. Would that be less offensive during gameplay? So if the rays are the same, then yeah, what you do is you get really, really bad flicker around in certain places and no flicker in other places. And that's not really a good trade-off, right? You don't want some of your lighting to be very accurate and some to be incredibly inaccurate. That's not so good. So what you want to do is something that minimizes the inaccuracy everywhere, so you get a consistent amount of flicker, if you will, and then you try to reduce that amount. It's the best way I could say it, I think. Oh, and one thing I should say, though, is along those lines, you will notice this I put in here. I did talk about removing some randomness. I do intend to remove some randomness, but only some. So what the stratified sampling stuff is about is saying, well, okay, let's suppose we want to take an integral along this hemisphere, right? And I know I've got to do random shots. Well, what I want to do is I want to partition it up into some parts and treat them as subintegrals, right? So I'm going to shoot rays randomly in here, 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 and only average along those, right? And so the way you do that is you just say, okay, every frame I'm going to shoot, 1, 2, 3, 4, 5, 6, 7 rays, and I'm going to constrain each ray to be random within its subregion. That's called stratified sampling, and that's a way of reducing the variance by saying, all right, look, we do know that we need to be random to try and pick up what's going on, but we want to try and reduce the randomness by keeping it within certain buckets. So we know we aren't, for example, on some frames just always sampling everything here and nothing out here, which would be a perfectly reasonable thing to happen with pure random rays. And so this is basically like going more towards the blue noise style sampling as opposed to white noise style sampling, for example. Would it be possible to cast cones instead of rays? Not into our geometry. There are ways you can do cone tracing into geometry that's better. Than ours. Now, we might be able to do something like cone tracing in the future with our spatial hierarchy, and that might be an interesting way to go, but we haven't quite gotten there yet. In order to cast cones and have it be any more efficient than casting rays, you need geometry that allows you to intersect a cone with it and return a color. And that's very difficult to do if you just have a bunch of sample points. So what you need to be able to do is aggregate those sample points up into larger areas so that when a cone hits them, you can just return just that one value, and we just haven't done quite that yet. So it may be possible in the future to cast, you may not be not cones per se, but they are like cones in that they are using coarser geometry as it gets further away to reduce variance. And yes, we may be able to do that with the spatial hierarchy, yeah. Do you currently do any form of ambient occlusion? Yeah, the lighting itself is actually solving for the ambient occlusion. We are not doing a special ambient occlusion pass to do... We have no hack in there for ambient occlusion at the moment, right? So we're actually solving for real ambient occlusion, no hacking. So just to be clear, because sometimes people have a special hack for ambient occlusion exactly, right? It's like a screen space prepass that just, guesses at what the ambient occlusion might be in that area. We're not doing that. But we do get ambient occlusion as part of the raycasting, so it is solving for that, right? if that makes sense. Giratoro, so you could use a blue noise-like source to select possible cones and shoot random rays inside each of these cones. Exactly. Or you don't even need to blue noise the cones. You can just use fixed cones. That has some consequences as well. You will see it a little bit. So I don't know exactly how we're going to do it, but yes. I mean, effectively that. What do you think about buying an IP that is practically abandoned by the publisher developer for a game that has about 100 players online at maximum? This is an online game. I have no idea. I'm a game engine developer. I don't know anything about that. Pile of poop. How much does each new light in the scene reduce performance? There is no reduction in performance for lights in the scene. It's flat rate. So you can have as many lights as you want. There's no performance change. It's purely based on the amount of geometry that there is. Off topic, do you feel like you still have the same passion for this project as you did back when you first began, or do some days feel more like it's a chore? I guess I don't know. I feel like that's a pretty broad question. If that makes sense. For the actual programming, no, I still like it. I guess is what I would say. All right, that's like about the end of the questions. So I'm sure it's best for maybe to some extent like Reflections AAA games do this, but are ray tracers really such a performance hit that they aren't used on more complex set of geometry games like Call of Duty or just in games with a lot of geometry? So yeah, raycasters and ray tracers just aren't really used because of the amount of geometry in most games. They're not common. What is common is using raycasting in situations to figure out something about light transport by doing the ray tracing on something else that's not the actual geometry in the game. So for example, there's screen space raycasting, and that gets used a lot. Like you said, Reflections in AAA games will do stuff like screen space ray tracing. And that's basically a way of saying, well, it's just too expensive to ray trace our geometry, but it's not necessarily too expensive to ray trace the pixels that we have, because there's a fixed number of those, and we can subsample them predictably and so forth, right? So, you know, that can happen. There's also stuff like pseudo-radiosity stuff, like Enlighten or whatever it's called. I don't know. That's a tech that got licensed by like Frostbite and stuff. And so, you know, there's that as well for real-time radiosity sort of stuff. That happens in a number of engines. Games that can oftentimes will bake lighting, but bake lighting is sort of a problem now for other reasons. So, you know, originally you always baked lighting, pretty much, period. And the reason you always baked lighting in was just because you couldn't do it any other way. Nowadays, pure baked lighting becomes less likely, largely for artist turnaround time. Light baking is a slow process offline as well. And so people have been looking for ways to speed up the, you know, having real-time or close to real-time lighting is not just something that allows the game to respond to changing lighting in the environment. It's something that helps artists produce better art. Because if the artists don't have to sit around waiting for the lighting to be recomputed, then they can see their changes more quickly and produce better artwork. So actually, in terms of ray tracing the lighting in sort of a slow offline fashion and using a bake, that's actually becoming less common for other reasons, right? That may have nothing to do with the actual runtime performance of the game. And so schemes that don't require that don't require slow offline bakes, are actually becoming more popular, not because of the game runtime, but actually because of the asset creation time. Do you have any good sources for learning about making lighting solutions? No, not really. How would we implement fog? Can we simulate different media in where the light propagates? Yeah, I don't know that you would really want to. I mean, yes, you could, but it's just going to add more noise, right? Is the problem. So I guess what I would say is you have to remember that something like fog, like participating media, requires you to take light that passes through it and randomly pick a point in the traversal region to bounce the light out randomly. That's just a huge source of noise, right? So if you actually wanted to simulate fog with this system in some way that was actually utilizing the system to fully do the fog, I think it would be way too expensive. I mean, we're already fighting to get the variance down just without stuff like that in there. So I would say if you did want to do fog, you might have to do something less rigorous than that and say, look, all we're going to do is when light passes through a fog area, we're just going to add light to the fog in that area, period. That's all we do. We don't bounce the light at all. So the fog doesn't contribute to the lighting solution. It only receives light from the lighting solution. That seems plausible, right? And similarly, the degree of attenuation in light that happens when it has to pass through fog, that could be done as well. Those two things I think would be fine. However, random scattering of light due to fog, I don't think is on the table. I just don't think that's feasible. So I think you could integrate fog into the system and do some interesting things. I don't think you could go all the way with it. That's just my guess. All right, that's about it. Okay, thank you everyone for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code, so you can follow along at home. That's about it for today. We'll be back next week when we will look at changing to bidirectional transport and stratified sampling just to see if we can get our variance down per frame before we go ahead and optimize ourselves some more with possibly doing maybe multi-threaded or GPU, or at the very least taking a look at our spatial hierarchy stuff and improving that, because we threw it in there and we've never really gone and given it the full sort of attention that it's going to need to be good. But yeah, pretty happy with the light. I'm liking it. I like the current one. That seems really stable. I'd like to reduce the variance a little bit, but it's, honestly, I don't know. If we optimized it, it might just be fine even the way it is right now. So we'll have to sort of continue on with the other parts of the lighting that need to get addressed, I think. All right, thanks for joining me, and I will catch you guys on the internet. Take it easy, everybody.